I want to start with a question that sounds simple. The kind of question you might brush off in about 3 seconds if I just asked it out loud, without any context. What if everything we thought we knew about how the universe ends is incomplete? Not a small miscalculation, not a small gap, wrong in a fundamental way. Wrong in the way that changes the answer from the universe expands forever to the universe might eventually collapse back on itself, and everything that has ever existed, every star, every galaxy, every atom, might one day be crushed back into a single unimaginable point. Wrong in the way that means the thing that has been quietly, invisibly, pushing the cosmos apart for 13.8 billion years is starting to slow down. In March 2025, 900 scientists from 70 institutions around the world published the results of a 3-year project that built the largest and most detailed and three-dimensional map of the universe ever created by human beings. They studied 15 million galaxies spread across 11 billion years of cosmic history. And what they found has not confirmed what we thought we knew. What they found has raised the very real possibility that the force governing the ultimate fate of everything in existence is not behaving the way our best theories said it should. Something is changing. And we are going to understand exactly what that something is. But before we get to the 2025 discovery, and before we get to the instruments and the data and the implications, I want to start somewhere much more personal, somewhere most science episodes never start. I want to start with a simple ball, because the ball is not a metaphor. The ball is actually the most important physics concept in this entire episode. And by the time we are done, you will understand exactly why the most fundamental question in astronomy was hiding inside something as simple as a childhood game. Imagine you are standing in a field, holding a simple soccer ball, and you throw it straight up into the air, as hard as you can. You already know what next. The ball rises, it loses momentum, it reaches its highest point, and then it falls back down, landing in your hand or somewhere near your feet. Every time, without exception, the gravity always wins. This is not something you learned. It is something you knew before you learned anything. It is built into your experience of existing in this world. Things thrown upward come back down. What if you threw that ball upward and, instead of slowing down, it started going faster? What if the higher it got, the faster it traveled? What if it left your hand at 10 meters per second, and by the time it was 100 meters up, it was doing 20 meters per second? And by the time it was a kilometer up, it was doing 50? And by the time you could not see it anymore, it was going so fast it was never coming back? You would not accept that. Your entire understanding of physics, the intuitive embodied physics you have carried since you were old enough to catch a ball, would tell you that something is wrong. Something is pushing it. Something invisible is accelerating it upward. That is exactly what happened to astronomy in 1998. For most of the 20th century, astronomers assumed the universe was like a ball. The Big Bang threw everything outward. Gravity was pulling everything back. The expansion should be slowing down. The question was not whether it would lose momentum. The question was whether gravity was strong enough to eventually stop the expansion and reverse it, or whether the ball had been thrown hard enough to escape gravity and drift outward forever at a diminishing rate. In 1998, independent teams of astronomers were measuring that deceleration, specifically measuring how much the expansion was slowing. They expected to find a number. The number that would tell them whether the universe would expand forever or eventually collapse. Instead, they found that the expansion was not slowing at all. It was speeding up. It means the ball was not slowing down. The ball was accelerating upward, faster and faster the higher it got, as if something invisible was pushing it from upward. That invisible push was given a name: the dark energy. And the three scientists who led those teams, Saul Perlmutter, Brian Schmidt, and Adam Rees, won the Nobel Prize in Physics in 2011. The dark energy changed everything. It meant the universe was not going to collapse. It was going to expand forever, faster and faster, until everything was so far apart that nothing could interact with anything else, and the universe faded into a cold, dark, empty void of maximum entropy. Scientists called this the Big Freeze, or the heat death, the long, slow fade. That was the answer for 25 years. The dark energy is a cosmological constant, a fixed property of space itself. It does not change. It does not weaken. The push is permanent. The ball is never coming back down. And then came 2025. Something has changed. The most detailed measurement of the universe's expansion history ever made is suggesting that the push might not be permanent after all. The push might be weakening. Your intuition about the ball might have been right all along, just delayed by 1 billion years. When people talk about the universe, they usually mean the visible universe. Stars, galaxies, nebulae, black holes, planets. The cosmic zoo of objects we have been cataloging and studying and marveling at for centuries. The Milky Way, Andromeda, the Hubble Deep Field, that famous image showing thousands of galaxies in a patch of sky the size of a grain of sand held at arm's length. All of that, every object ever observed, every photon ever detected, every star ever named, is approximately 5% of the total mass and energy content of the universe. 5%. I want you to sit with that for a moment, because it is genuinely extraordinary. The remaining 95% falls into two categories that together represent the deepest unsolved mystery in all of modern physics. 27% is dark matter, invisible, undetectable by any telescope ever built, because it does not interact with light in any way we can currently measure. It does not shine, emit, absorb, or reflect radiation, but it has gravity. We know it exists because of what it does to the things we can see. Galaxies rotate in ways that only make sense if there is an enormous invisible mass holding them together. The way the light from distant galaxies bends as it passes by clusters of other galaxies cannot be explained by the visible mass alone. There has to be more mass that we cannot see. Dark matter is the gravitational scaffolding of the universe. Without it, galaxies would fly apart. Without it, the large-scale structure of the cosmos, those vast walls and filaments of galaxy clusters that look from a distance like a cosmic spider web, could not have formed. We have never detected a single dark matter particle directly. Not one. Decades of exquisitely sensitive underground detectors, built specifically to catch the faint whisper of a dark matter particle passing through a tank of liquid or a crystal of germanium. Nothing. The dark matter is there. We know it is there. We just cannot catch it. And then there is the remaining 68%. Dark energy, not dark matter. They share the word dark, but they are completely different things. Dark matter is a substance, something with mass that fills space. Dark energy is a force, or a property of space, or a field, or something we do not have a satisfying word for yet. Dark energy does not pull things together. Dark energy pushes things apart. It is the force behind the accelerating expansion, the invisible push beneath the ball. And of the two great unknowns, dark energy is the one that keeps physicists up at night. Not because it is more mysterious than dark matter. Both are deeply mysterious. But because dark energy makes up more of the universe than everything else combined. And because what happens to dark energy determines what happens to everything. To the whole thing. All of it. Forever. Here is the standard explanation you get in science documentaries and textbooks. Dark energy is the cosmological constant, Einstein's lambda, a constant energy density that fills space uniformly, the same everywhere and at all times. It is simply a property of empty space. The vacuum has a non-zero energy, and that energy manifests as a repulsive pressure that drives expansion. Clean, simple, mathematical. The cosmological constant fits the observations beautifully. There's just one problem. A catastrophic, embarrassing, deeply unresolved problem that sits at the heart of theoretical physics and has never been solved. When you calculate from quantum field theory, our best theory of the very small, what the vacuum energy of space should be, you get a number. It is not a small number. The vacuum energy of space, according to quantum mechanics, should be approximately 10 to the power of 120 times larger than what we actually observe. 10 to the power of 120. That is a 1 followed by 120 zeros. For context, the total number of atoms in the observable universe is estimated at around 10 to the power of 80. The discrepancy between the theoretical prediction and the observed value of dark energy is 40 orders of magnitude larger than the number of atoms in the entire observable universe. This is called the fundamental constant problem, and it is arguably the worst prediction in the history of physics. The theory and the observation disagree by a factor so enormous it stops being a number and starts being an indication that something is fundamentally wrong with how we are thinking about the question. Physicists have tried many approaches to resolve this problem. Supersymmetry, string theory, extra dimensions, modified gravity. So far, none of them has produced a satisfying resolution. Yet, on top of this already deeply uncomfortable problem, DESI is suggesting that dark energy is not even constant. It is changing, which means that even the description of dark energy that we were using, however uncomfortable its theoretical underpinnings, may not be accurate. We are not at the edge of understanding dark energy. We may be further from understanding it than we realized. And that is actually exciting, not depressing. Because the places where our current theories fail are exactly the places where the next great theory begins. So how you map 15 million galaxies? Kitt Peak, a mountain in the Sonoran Desert of Arizona. Elevation 2,096 meters. On a clear night, from the summit, you can see the lights of Tucson glowing on the horizon, and above you a sky with almost no light pollution. Thousands of stars visible with the naked eye. The Milky Way a pale smear from horizon to horizon. On that mountain sits the Nicholas U. Mail telescope, a 4-meter reflector built in the 1970s, recently retrofitted with an extraordinary new instrument called DESI, the Dark Energy Spectroscopic Instrument. DESI has 5,000 robotic optical fibers arranged across its focal plane. Each robot, each tiny fiber positioner, can be commanded to move to a specific position, targeting a specific galaxy, with a precision of better than 1/10 of the width of a human hair. In a single pointing of the telescope, DESI simultaneously captures light from 5,000 different galaxies. Each fiber feeds the light from its galaxy to a spectrograph, a device that spreads light into its component wavelengths, like a prism breaking white light into a rainbow. The spectrograph produces a spectrum for each galaxy, a fingerprint of light that reveals the galaxy's chemical composition, its temperature, and most importantly, its redshift. Redshift is the key. When a source of energy is moving away from you, the waves of light get stretched, shifted toward the red end of the spectrum. The faster the source is moving, the more the light is redshifted. By measuring a galaxy's redshift precisely, astronomers can calculate how fast it is moving away from us. And because the universe is expanding uniformly, every galaxy moving away from every other in proportion to the distance between them, the recession speed is directly related to the distance. Measure the redshift, calculate the recession speed, and you know how far away the galaxy is. Distance in space is time. A galaxy 5 billion light years away is showing you what the universe looked like 5 billion years ago. A galaxy 10 billion light years away is a window into a universe half its current age. By mapping galaxies at a range of distances, DESI is not just mapping where things are, it is mapping when things were. A three-dimensional map is also a time machine. In 3 years of operation, DESI observed approximately 15 million galaxies and quasars, the luminous, energetic cores of active galaxies powered by supermassive black holes, spanning from nearby galaxies just hundreds of millions of light years away to galaxies so distant their light left them when the universe was less than 3 billion years old. The result is the largest and most detailed three-dimensional map of the universe ever created. A map that reveals, in extraordinary detail, how the universe has been expanding at every point in the last 11 billion years. And somewhere in that map, hidden in the subtle pattern of how galaxies are distributed across cosmic time, is the signal that has changed everything. To extract the history of dark energy from this galaxy map, DESI uses a technique called baryon acoustic oscillations. And I want to explain this properly because it is one of the most beautiful ideas in astronomy. 13.8 billion years ago, the universe was born in the Big Bang. For the first 380,000 years, it was a hot, dense plasma. The protons, the electrons, and photons all interacting with each other in a turbulent soup of energy. Pressure waves rippled through this plasma. Giant acoustic waves, sound waves, in a sense, though not sound as we experience it, propagating through the entire early universe. Then, 380,000 years after the Big Bang, the universe cooled to the point where the electrons and the protons could combine to form hydrogen atoms. The plasma became a gas. The photons, suddenly freed from their constant interactions with charged particles, streamed outward in all directions. This is the moment when the cosmic microwave background was created. The oldest light in the universe, still detectable today as a faint microwave echo coming equally from every direction in the sky. And the pressure waves? They froze. The moment the plasma became a gas, the waves stopped. They were imprinted in the distribution of matter, a preferred distance between concentrations of matter, a subtle but measurable pattern where galaxies are slightly more likely to be separated by a specific distance than by other distances. That preferred distance is approximately 490 million light years. And it is the same everywhere and at every time. It is a standard ruler baked into the fabric of the universe since 380,000 years after the Big Bang. This is the brilliant part. If you know the true length of a ruler, and you can measure how long it appears to be at different distances, you can calculate how much the universe has expanded between then and now. Measure the apparent size of the acoustic ruler at different epochs, different redshifts, and you can reconstruct the expansion history of a universe in detail. You can see how fast the universe was expanding 1 billion years ago, 2 billion years ago, 5 billion, 10 billion. You can trace the history of dark energy across cosmic time. This is what DESI did with 15 million galaxies. And what they found was not a straight line, not a constant, not the fixed push of a cosmological constant. Something was changing. The discovery that changed everything. The DESI collaboration, 900 scientists, 70 institutions, years of work, presented the results of their first 3 years of data. The presentation was careful, scientific, precise. The headline was, "Dark Energy May Be Weakening Over Time." Underneath that careful headline was something that, if confirmed, will be one of the most significant scientific discoveries of the 21st century. Let me walk you through what the data actually says. In the mathematical framework of the dark energy, there's a parameter called W, the equation that defines of dark energy. In the classical constant model, the standard model, W is exactly -1. Always. Everywhere. That fixed value is what gives you the constant push. The steady acceleration. The ball that never comes back down. When DESI combined their galaxy survey data with 3 other independent measurements, the cosmic microwave background, observations of type I supernovae, and the pattern of how mass is distributed on large scales, they found that the data fits better with a value of W that changes over time. Specifically, a value of W that suggests dark energy was stronger at the beginning and is weaker now. Go back to the ball. For 25 years, we thought someone was pushing the ball with a perfectly constant force. Same push in 1998. Same push in 2010. Same push today. The push of our original constant. What DESI is saying is, the push has been getting weaker. Not dramatically. Not a sudden change. A gentle, gradual, but measurable weakening over billions of years. The push that has been driving the universe's acceleration is fading. And if it fades enough, if it continues to weaken, at some point gravity starts to win again. The ball loses momentum, stops and falls down. What dark energy actually means. Let me be specific about that distinction because it matters. We know dark energy exists because of its effects. The accelerating expansion is real. The DESI map is real. The data is real. Something is causing the universe to expand faster and faster. And whatever that something is, we call it dark energy. But the name is a placeholder, a label for our ignorance. We call it dark energy for the same reason we call the invisible scaffolding dark matter, because we cannot see it, and because naming something is the first step toward understanding it, even if the name itself contains no information. The question of what dark energy actually is, what it is made of, why it exists, where it comes from, what it will do in the future, remains completely unanswered. And the DESI results have made the question simultaneously more urgent and more open. Here are the serious contenders. The simplest explanation is still the one Einstein accidentally introduced in 1917. The classical constant, a fixed, unchanging energy density inherent to empty space. The vacuum energy. Space is not nothing. It has force simply by virtue of existing, and that force manifests as a gentle repulsive pressure. This fits the observations. For 25 years, it has fitted the observations beautifully. The problem is theoretical. Quantum field theory, our best theory of matter and energy at the smallest scales, predicts that the vacuum should be seething with energy. Virtual particles constantly popping in and out of existence, contributing to the total energy density of empty space. When you add up all those contributions, you get a number for the vacuum energy density that is approximately 10 to the power of 120 times larger than what we observe. If the vacuum energy were actually that large, the universe would have expanded so violently in its earliest moments that no structure could ever have formed. Atoms could not have clumped together. Stars could not have ignited. Galaxies could not have assembled. Life could not have emerged. The classic constant problem, this 10 to the 120 discrepancy, is the most extreme mismatch between theoretical prediction and experimental observation in the history of science. Nobody has a satisfying explanation for why the classic constant is so extraordinarily small compared to what quantum mechanics says it should be. Some invoke a mechanism called supersymmetry cancellation, quantum contributions of opposite sign canceling to an extraordinary degree of precision. Some invoke the anthropic argument. We observe a small classic constant because only in universes with small classic constants does life exist to observe anything. Neither is fully satisfying. And at this moment DESI is suggesting it might not even be constant, which means the classic constant might not be the answer at all. Quintessence is the idea that dark energy is not a fixed property of space, but a dynamic field that fills all of space and evolves over time. Like other fundamental fields in physics, the electromagnetic field, the Higgs field, quintessence is a field whose value changes over space and time. But unlike those fields, quintessence is extremely weakly coupled to ordinary matter, which is why we have not detected it in particle accelerators or laboratory experiments. The energy density of a quintessence field can decrease over time. If dark energy is quintessence, then the DESI results make perfect sense. The field was stronger in the past, providing a larger accelerating push. It is weaker at this moment. It will continue to weaken. And eventually, perhaps, it weakens enough that gravity dominates and the expansion reverses. The ball comes back down. Quintessence is the most popular alternative to the classic constant among cosmologists. It is consistent with the data. It has a theoretical basis in quantum field theory, and it naturally produces a dark energy that evolves over time rather than remaining constant. The challenge is that quintessence requires fine-tuning of its own. The mass of the quintessence field needs to be extraordinarily small to produce the observed behavior of dark energy. And we have no confirmed candidate from particle physics for what the quintessence particle or field actually is. Phantom energy. This is the unsettling one. Phantom energy is a hypothetical form of dark energy that behaves in the opposite way to quintessence. Instead of weakening over time, it strengthens. Its energy density increases as the universe expands. If dark energy is phantom energy, the future of the universe is not a big freeze or a big crunch. It is a big rip. As dark energy strengthens, it eventually overcomes not just the gravity between galaxy clusters, but the gravity within individual galaxies. Galaxies are shredded. Then individual star systems are disrupted. Planets are torn from their orbits. Eventually, the atomic forces holding matter together are overwhelmed. Molecules dissociate. Then atoms. Then atomic nuclei. Then the quarks inside protons and neutrons are pulled apart by the expanding fabric of space itself. In the final fraction of a second before the Big Rip, the universe tears itself apart at the most fundamental level. The DESI data currently argues against phantom energy. The signal suggests dark energy is weakening, not strengthening. But the data is not definitive. Dark energy could be weakening at this moment and strengthen again in the future. We have no complete theory that predicts what it will do. Modified gravity. Perhaps there is no dark energy at all. Perhaps what we are calling dark energy is actually a sign that our theory of gravity, Einstein's general relativity, breaks down at classic scales. That the accelerating expansion is not caused by an energy field, but by gravity itself behaving differently on the largest scales than it does in our local cosmic neighborhood. Modified gravity theories have been proposed. Most of them struggle to reproduce the full picture of standard observations as accurately as the classic constant. But they cannot be completely ruled out. If dark energy is modified gravity rather than a real energy field, then the DESI measurement of apparent dark energy evolution could be measuring the scale at which general relativity deviates from its predictions, not the properties of a real physical substance. It is an unsettling possibility because it would mean that not only do we not understand 68% of the universe, we also do not fully understand gravity, the force that has been the foundation of cosmos since Isaac Newton. The three possible ends of everything. The fate of the universe depends entirely on what dark energy does in the future. And right at this moment, thanks to DESI, we genuinely do not know. So let us walk through all three possibilities clearly. The big freeze, the long silence. This was the dominant prediction for the last quarter century. If dark energy is a standard constant, if the push remains steady and permanent, this is what happens. The universe continues to expand forever at an accelerating rate. The distances between galaxy clusters grow. The Milky Way and Andromeda will merge in about 4 to 5 billion years. That collision is coming regardless of dark energy. It is too close for the expansion to prevent it. But beyond our local group of galaxies, everything is moving away. And as dark energy keeps pushing, the expansion accelerates to the point where galaxies beyond our local group move away from us faster than light. Not because they are moving through space faster than light. Nothing moves through space faster than light, but because the space between us and them is expanding so fast that the net effect is a recession speed exceeding the speed of light. The light from those galaxies can never reach us. They disappear beyond our cosmic horizon. The observable universe shrinks. Over trillions of years, our local group becomes our entire observable cosmos. Beyond it, nothing. Not darkness, just the absence of any signal, any information, any connection. Stars burn through their fuel. The last massive stars die within tens of millions of years. Red dwarfs, the smallest and most fuel-efficient stars, burn for up to 10 trillion years. Nearly 1,000 times the current age of the universe. Eventually, even they go dark. After approximately 10 to the power of 14 years, 100 trillion years, the last star in our galaxy flickers out. The Milky Way, once blazing with hundreds of billions of suns, is a cold, dark collection of stellar remnants. White dwarfs slowly cooling toward the temperature of the surrounding space. Neutron stars, black holes. Over inconceivable timescales, the black holes grow as they absorb the remaining dark matter and stellar remnants. Eventually, through a process called Hawking radiation, the quantum mechanical evaporation of black holes predicted by Stephen Hawking, even the black holes dissipate. The most massive black holes, containing billions of solar masses, take approximately 10 to the power of 100 years to evaporate, a number so large that it is, for all practical purposes, eternal. What remains is a universe of dispersed elementary particles, photons, neutrinos, and the occasional electron and positron, spread across an incomprehensibly vast expanding void, growing colder, growing dimmer, approaching but never quite reaching absolute zero and thermodynamic equilibrium. This is the heat death, the maximum entropy state, the cold, dark, structureless final condition of an eternally expanding universe. Not a dramatic end, not a bang, not a crunch, just a fade. The longest, quietest death imaginable. The ball thrown so hard, with such a permanent upward push, that it rises forever and never returns. The big crunch, the return. This is what the DESI data is now putting back on the table for the first time in a generation. If dark energy is weakening, if the push is fading, at some point gravity reasserts itself. The expansion slows, stops, reverses. This process would begin on the largest scales. The great cosmic web of galaxy filaments and voids, the large-scale structure of the universe, would start to evolve differently. Instead of growing, it would begin to compress. Galaxy clusters that have been drifting apart would slow their separation. Eventually, the drift reverses. The sky changes. Distant galaxies that were redshifted, their light stretched by the expanding universe, gradually shift toward blue. They are approaching instead of receding. Over billions of years, the universe contracts. Structure collapses on the largest scales first. Galaxy clusters merge into superclusters. Superclusters merge into even larger structures. The previously vast voids between filaments of galaxies begin to fill as matter falls inward under gravity. Individual galaxies are forced together more frequently. Stellar collisions become common. The star formation rate surges as gas clouds are compressed by the increasing density and temperature of the universe. As the contraction accelerates, the cosmic microwave background, which has been cooling for 13.8 billion years as the universe expanded, begins to heat up again. The background radiation temperature rises above the temperature of stellar surfaces. Stars are not simply radiating heat into a cold void. The universe itself is hotter than they are. Stars dissolve into the ambient plasma. Everything that has ever existed, every structure, every atom, every photon, is compressed into an increasingly dense and hot singularity. The Big Crunch, the mirror image of the Big Bang. And then? We do not know. This is where our physics breaks down. At the singularity, a point of infinite density and temperature, general relativity ceases to give meaningful answers. What happens at the singularity requires a quantum theory of gravity that we do not yet have. Some models suggest the collapse does not reach a true singularity, but instead bounces. A new Big Bang emerging from the maximum compression of the old universe. The cyclical universe. The bouncing cosmos. Each universe born from the collapse of the previous one. Expanding, slowing, contracting, bouncing, expanding again. Our Big Bang was not the beginning. It was a rebound. And our Big Crunch, if it comes, will not be the end. It will be a reset. The ball goes up. The ball comes back down. And from the impact of that return, a new ball is thrown. This is not established science. It is a speculative model, but it is a scientifically serious one. And it becomes more compelling if the DESI data holds up. The Big Rip. This is the most dramatic and viscerally unsettling of the three fates, though the one that current data argues least in favor of. If dark energy is not weakening but strengthening, if the push gets harder as time passes, then the future of the universe does not end in silence or collapse. It ends in violent disintegration. As dark energy strengthens, it eventually overcomes the gravity, holding galaxy clusters together. Clusters disperse. Then individual galaxies are torn apart. The Milky Way is shredded, its stars flinging outward as dark energy overwhelms the gravity that held them in their orbits for billions of years. Then stellar systems. The planets of individual stars are pulled from their orbits. The Earth is torn from the sun's gravity. The moon is pulled from Earth. All of this happens, according to some models, in a cascade that occurs in the final billion years before the Big Rip. Then, in the final million years, gravitational forces within individual planets are overwhelmed. The Earth disintegrates. In the final minutes, individual molecules are torn apart. Then atoms. Then atomic nuclei. The strong nuclear force, which binds protons and neutrons together with extraordinary strength, is overwhelmed. Protons, and neutrons dissolve. In the final fractions of a second, even quarks, the fundamental constituents of protons and neutrons, are separated by the accelerating expansion of the fabric of space itself. The Big Rip happens in finite time. Some estimates put it at approximately 22 billion years from now, though this depends critically on how dark energy behaves. In the final moment, the universe tears itself apart at every scale simultaneously. As I said, the current DESI data argues against this fate. The signal suggests dark energy is weakening, not strengthening. But dark energy could weaken now and reverse later. We have no theory that forbids it. The future of dark energy is, right now, unknown territory. What happens the day we actually understand dark energy? Not just measure it, not just map its effects across 11 billion years of cosmic history, but truly understand it. Know what it is made of. Know where it comes from. Know why space itself has this intrinsic energy and how it behaves and why it is changing. What does that day look like for human civilization? To answer that properly, I need to introduce you to an idea proposed in 1964 by a Soviet astronomer named Nikolai Kardashev. It is called the Kardashev scale, and it is one of the most useful frameworks ever invented for thinking about the long-term future of intelligent civilization. Kardashev was thinking about how to search for extraterrestrial intelligence. He asked a simple question: if there are other civilizations in the universe, how will we classify them? How do we measure the advancement of a civilization in a way that is objective, universal, and meaningful? His answer was energy. The most fundamental measure of what a civilization can do is how much energy it can access, store, and use. From that insight, he defined 3 levels. A Type 1 civilization has mastered all the energy available on its home planet. Every source of energy the planet provides — solar, geothermal, wind, tidal, nuclear — is fully harnessed and used with complete efficiency. No energy is wasted. No resource is untapped. The total energy available to a Type 1 civilization is approximately 10 to the power of 16 watts. 10,000 trillion watts. Human civilization currently uses approximately 2 times 10 to the power of 13 watts, about 20 trillion watts. We are roughly 0.7 on the Kardashev scale. Not yet Type 1. Close, but not there. The physicist Michio Kaku estimates we will reach Type 1 status within the next 100 to 200 years, assuming we navigate the challenges ahead. A Type 1 civilization controls its weather. It manages geological activity. It prevents asteroid impacts. It has essentially conquered its home planet and turned it into a fully managed living system. We are approaching Type 1. Slowly, unevenly, but the trajectory is there. A Type 2 civilization has mastered all the energy output of its star. Not just the small fraction that falls on their planet. All of it. Every photon, every particle, every watt of energy the star produces is captured and used. The mechanism most often proposed for this is a Dyson sphere, a structure, not necessarily a solid shell, but perhaps a swarm of satellites or collectors, built around the star to capture its total energy output. The Sun outputs approximately 3.8 times 10 to the power of 26 watts. A Type 2 civilization harvests all of that. The energy available is 10 billion times greater than what is available to a Type 1. With that energy, a civilization could reshape planets, build structures on a scale that dwarfs anything we currently conceive of, travel between stars, not in centuries, but in time frames that make interstellar travel practical. A civilization that has harnessed its star is effectively immortal on any human timescale. It is no longer vulnerable to the death of its home planet or any natural catastrophe that does not destroy the star itself. A Type 3 civilization has mastered the energy of an entire galaxy. Not one star. All of them. The Milky Way contains somewhere between 200 and 400 billion stars. A Type 3 civilization has harnessed all of that energy, has spread across the galaxy, built around its stars, and commands energy resources 100 billion times greater than a Type 2. At this scale, the physics of what is possible becomes almost incomprehensible. Manipulating space-time itself becomes conceivable. Moving stars, preventing supernovae, engineering the large-scale structure of the galaxy. A Type 3 civilization operates on timescales and spatial scales that make the entire history of human civilization look like a single heartbeat. And here is where dark energy enters the picture, in a way that changes everything. There is a fundamental problem with the Kardashev scale beyond Type 3. If you have harnessed your entire galaxy, where do you go? What is the next level? The answer, if you follow the logic of the scale, is the universe itself. A Type 4 civilization would harness the energy of all 2 trillion galaxies, all their stars, all their matter, all their energy. But there is an obstacle, and that obstacle is dark energy. Dark energy is causing the universe to expand at an accelerating rate. As time passes, the galaxies beyond our local group are being carried away from us faster and faster by the expansion of space. Within the next few tens of billions of years, those galaxies will be moving away faster than light can bridge the gap. They will disappear beyond our cosmic horizon, permanently, irretrievably. The energy in those galaxies, the stars, the matter, the potential, will be forever inaccessible. Not because of any technological limitation, because the universe itself will have placed them beyond reach. A civilization aiming for Type 4 is running against the clock, and that clock is dark energy. Every year that passes, more of the universe's energy becomes permanently inaccessible as distant galaxies cross beyond the horizon. The window to expand fast enough to reach those resources before dark energy takes them away is finite, and it is shrinking. But here is the pivot that connects everything. What if we could understand dark energy well enough to interact with it? What if dark energy is not just the obstacle, but the key? Let me be clear about what I am about to say. What follows is scientifically grounded possibility. Ideas that emerge naturally from our current understanding of physics, but that go beyond confirmed knowledge. The verified science ends here. What follows is informed imagination, not established fact. With that said, here is what becomes conceivable if we crack dark energy. Dark energy is the energy of the vacuum. Empty space has energy simply by existing. That energy, according to quantum field theory, should be almost incomprehensibly larger than what we observe. Something is suppressing it. Some mechanism we do not understand is holding almost all of that energy in check, allowing only a tiny fraction to manifest as the dark energy we measure. If we understood that suppression mechanism, if we understood why the vacuum energy is so extraordinarily small compared to what the theory predicts, we might be able to interact with it, not necessarily to extract it directly, but to understand the conditions that determine it. And a sufficiently advanced civilization that understands those conditions might be able to manipulate them locally. The first implication is propulsion. Dark energy is what causes space itself to expand. A civilization that could manipulate the local curvature of space, using something analogous to dark energy, could in principle create a region of expanding space behind a spacecraft and contracting space in front of it. This is the theoretical basis of the Alcubierre warp drive, a concept published in 1994 that is consistent with general relativity but requires exotic energy sources with properties similar to dark energy. Understanding dark energy would not give us warp drives tomorrow, but it would tell us whether they are physically possible or permanently forbidden. Right now, we genuinely do not know, and not knowing means we cannot even begin to build toward the answer. The second implication is energy itself. If the vacuum energy is as large as quantum mechanics suggests, if something is suppressing 10 to the power of 120 times the observed value, then space itself is an energy reservoir of incomprehensible scale. A civilization that learned to access even a tiny fraction of that suppressed vacuum energy would have effectively unlimited energy, not from stars, not from matter, from the fabric of space itself. Such a civilization would not need a Type 2 or Type 3 progression at all. It would represent a category the Kardashev scale does not even include. The third implication is control over the expansion itself. A deep understanding of dark energy would be a deep understanding of why space expands and what determines the rate. With that understanding might come the ability to locally counteract the expansion, to prevent the universe from carrying away the resources needed for long-term civilizational survival. A sufficiently advanced civilization might not need to race against the expanding cosmos. It might be able to hold the cosmos still. Here is the most important thing I want to say about all of this. In 1865, James Clerk Maxwell published his unified theory of electricity and magnetism. 4 equations describing the behavior of electromagnetic fields with complete accuracy. Nobody at the time imagined radio. Nobody imagined television, wireless communication, mobile phones, the internet, or the electromagnetic infrastructure that modern civilization is built upon. The applications were unimaginable because the technology to use the knowledge did not exist yet. That technology was built by generations of engineers who were not yet born, working on problems that had not yet been defined. The same pattern holds for every fundamental discovery in physics. Quantum mechanics was developed in the 1920s. The transistor, which makes every computer in existence possible, came in 1947. The laser came in 1960. GPS, which requires relativistic corrections to function, came in 1994. Understanding always came first. Applications followed, decades later, in ways the original scientists could not have anticipated. Dark energy was confirmed to exist in 1998. We do not yet understand what it is. We are at the stage of Maxwell in 1860. We have equations that describe the behavior, but we do not yet understand the underlying reality. The equivalent of Maxwell's unification, a true theoretical understanding of dark energy, has not happened yet. When it does, the applications will come, in ways we cannot predict, on timescales we cannot know. But if the pattern of physics history holds, and it has held every single time, the applications will be extraordinary in ways that make our current imagination look small. The Kardashev scale describes civilizational progression in terms of energy mastery. We are approaching Type 1. Type 2 requires stellar engineering. Type 3 requires galactic expansion. And beyond that, the step where dark energy becomes both obstacle and possible key is mastery of the universe itself. But there may be a different kind of progression, not just more energy from the same sources. Access to entirely new categories of energy that previous levels did not know existed. Before quantum mechanics, a civilization maximizing its energy would focus on fire, mechanical power, and eventually steam. The idea of splitting an atom to release the energy binding its nucleus together was not just technologically impossible, it was literally inconceivable. The energy was there, always there, in every atom of matter in the universe, but invisible, inaccessible, not because the technology was missing, because the understanding was missing. Dark energy might be exactly the same kind of threshold, not a new source of energy in the conventional sense, a new category entirely, energy that is not in matter, not in stars, not in chemical or nuclear reactions, but in space itself, everywhere, always, in incomprehensible abundance. And we are, right here in 2025, at the moment when the first serious cracks are appearing in our ignorance about what it is. DESI has found that dark energy is not what we thought. It is changing. It is dynamic. It has a history, and it will have a future. That means it is not simply a fixed property of reality we have to accept and work around. It is something that evolves, something that responds to conditions, something that potentially could be understood deeply enough to be worked with. We are not about to harness dark energy. We are not on the verge of warp drives or vacuum energy extraction. We are at the stage of noticing, for the first time, that the thing we called a cosmological constant is not actually constant. That is the very beginning, the first step of a journey whose destination we cannot yet see. But every great journey in physics started exactly here, with an observation that something is not behaving the way the current theory says it should, with a measurement and a model that disagree. And in that gap, in that quiet, technically precise, deeply unsettling gap, the next chapter of human understanding begins. We're standing in that gap right now. What we build from it, what human civilization eventually constructs from whatever understanding emerges, is something none of us alive today will fully see. But we are the generation that found the gap, and that is not nothing. The dark energy is not constant. It was stronger when the universe was young. It is weaker right this moment. The push beneath the ball is fading. Not confirmed. Not yet at the threshold of discovery. But real enough, significant enough, that the co-spokesperson of the team that found it stood in front of the American Physical Society and said, "We may be on the cusp of a major discovery about dark energy and the fundamental nature of our universe." And a physicist on that same team said something quieter and stranger. He said, "There is the possibility that everything comes to an end. Will we consider that a good or bad thing? I don't know. A scientist, measuring the universe, finding that it might eventually collapse back on itself, and genuinely not knowing whether that is good or bad." I think about that statement a lot. What the DESI data opened was not an answer. It opened 3 doors, and we do not yet know which one leads to the truth. Behind the first door, the push holds. Dark energy stabilizes. The expansion continues forever, gently, without acceleration. The universe coasts into the big freeze. Every star burns out. Every black hole evaporates. The cosmos fades into the longest, quietest silence imaginable. Not dramatic, not violent, just a fade. The ball, slowing at last, drifting upward forever into the dark. Behind the second door, the push fades completely. Gravity wins. The expansion slows, stops, reverses. Everything that has been drifting apart for billions of years begins, almost imperceptibly, to drift back together. Galaxies merge. Stars dissolve. The universe contracts back toward the conditions of the Big Bang. And perhaps, if the bouncing universe models are right, it does not end there. Perhaps the collapse reaches its minimum and rebounds. A new Big Bang. A new universe. Our entire cosmic history. Every star, every planet, every moment of life and thought and discovery, becoming the seed of something new. The ball coming back down at last, hitting the ground and bouncing into a new sky. Behind the third door, the data is noise. More measurements from DESI, from Rubin, from Euclid, from Roman, show that dark energy is constant after all. The standard model survives. The big freeze was always the answer. And the signal that shook science in 2025 turns out to be a ghost in the data, a statistical whisper that larger data sets will silence. We do not know which door is the right one. Nobody does. The universe will keep expanding while you rest. And somewhere, and the data is still being collected, the answer is waiting.